To introduce this program on Halleys Comet, I'm out here on the western plains of New South Wales, out near Parkes. The sun's just up and it's been a bit chilly. I'm out here for two reasons, really. The first is that this part of New South Wales, west of the Great Divide, with wide flat horizons and dark clear skies, is really ideal comet watching territory. The local tourist industry, the motels and souvenir shops, are hoping to make quite a nice profit over the next month or two, serving the tourists who come here in droves, hoping to get a glimpse of the comet. But I must say that even out here, it's not easy to see the most famous comet of all. I was out about 3 hours ago when it was still fully dark, and I looked in the east, and to be sure I could see the comet hanging there against the stars, rising before the dawn, but it was pretty close to the limit of visibility, and certainly was not the spectacular sight that it was last time Halleys Comet came by in 1910. But even though this visitation will be a disappointment for you and me with just our eyes or perhaps a pair of binoculars, it'll be a bonanza for the boffins. They're really ready. This time around, Halleys will be the most intensely studied comet in history. Over the last month or so, a whole armada of spacecraft from a number of nations have rendezvoused with the comet in space, gathering scientific information, taking pictures, sending them back, harvesting a whole cornucopia of data on what makes a comet tick. Now, one of those probes was Giotto, launched by the European Space Agency and programmed to fly right through the head of the comet. And that's the second reason that I'm here, because this great radio telescope, run by the CSIRO out here at Parkes, is the ear of Giotto. It's the point of contact between the spacecraft in the depths of space and its handlers here on Earth. Without this telescope, there would really have been no mission. On the morning of the encounter, the telescope swung over well before dawn to acquire the signal from Giotto as it rose above the eastern horizon. The signal was then processed through the control rooms here and sent on to Darmstadt in West Germany, where the nerve centre for the entire operation is. As the encounter developed throughout that morning, Friday the 14th, our time, the BBC was on hand in force. At Darmstadt itself, the well-known broadcaster and writer on things astronomical, Patrick Moore. And at the old observatory buildings at Greenwich, James Burke. Let's join them now.
The object of this night's mission is to follow Giotto all the way in. At the present moment, it's something like 250,000 kilometres away from the nucleus of the comet. At closest approach, in just over an hour's time, it'll only be 540 kilometres away. And it's then, if at all, that we're going to see the nucleus. We've simply got to wait and see. Halleys Comet is named in honour of the second Astronomer Royal, Edmund Halley. His headquarters was at Greenwich, at the Royal Greenwich Observatory, where James Burke now is. James.
Thank you, Patrick. Well, I'm here on what is a bitterly cold night at Greenwich because it was here, in a sense, where the original scientific interest in the comet Halley really got going. And I'm here especially to look at the technology behind tonight's literally once-in-a-lifetime encounter, the encounter between the spacecraft Giotto and the comet called Halley. That we are able at all to rendezvous with a comet travelling at 68 kilometres a second, 230 million kilometres out in space, is mainly due to the original predictions by Edmund Halley, England's second Astronomer Royal, here some 300 years ago. The latest of his successes is with us tonight, here in the Octagon Room, where the earliest observations were made. Professor Sir Francis Graham-Smith, the 13th Astronomer Royal, is watching these events with his guests, who include Professor Alec Boxenberg, Director of the Royal Greenwich Observatory at Hurst-Wonso, and other experts in what we'll loosely call tonight cometry. We'll be talking to them later. As Giotto races towards the encounter at about 70 times the speed of a bullet, I will be taking a look at the onboard instruments, and in particular at that camera that we hope will answer fundamental questions, not just about Halley, but perhaps about the origins of the solar system and even the origin of life on Earth. I say we hope for two good reasons. One, Giotto may not survive the journey to the heart of the comet to take those first ever pictures of its nucleus. And two, even if it does, the pictures that the two Russian spacecraft that went past the other day made it all look pretty dicey. The situation as they saw it makes us feel that tonight the encounter may turn out to be a more dangerous event than was perhaps foreseen. But more of those problems later on, because right now The spacecraft is heading into the comet's coma, a giant cloud of gas and dust surrounding the nucleus. And since Giotto's encounter speed is about 240,000 kilometers an hour, every tiny dust particle will hit Giotto like a bullet. This is what the spacecraft looks like as it heads for Halley, like this, with its dust shield forward. And as we go through the evening, I hope we will be able to see the build-up of computer-generated data showing the dust impacts actually hitting the shield at the time. The point is, will that dust shield work? Well, you'll be able to see the answer to that, as I said here, as the onboard impact sensors feed back second-by-second data on the kind of punishment that Giotto's taking. If the sensors themselves aren't destroyed, that is. Initially, that data and all the rest is coming in from space to a huge radio telescope in Australia and then to the European Space Operations Centre, Patrick.
Which is where I am now, at the headquarters of the European Space Agency. This is where the information from the comet is being received, but the real action's taking place over 90 million miles away. Here's the science area. We'll be meeting some of the principal investigators during the course of the night. And of course, there's the control room, which recently had the job of directing the spacecraft to its precise distance from the nucleus. But since the Russian and Japanese encounters, there's been a great deal of controversial discussion among the scientists here as to what that distance should be. We know that at the moment, Giotto is inside the coma, but outside the main dust area. What exactly is a comet? Basically, it has a nucleus, described as a dirty ice ball, which is the only reasonably massive part. When the ices are warmed, they start to evaporate, and the nucleus hides itself inside the head or coma, which is why we've never yet seen a cometary nucleus, something we'd like to rectify before this program's over. There are two types of tails. The plasma, or gas tail, is caused by the solar wind striking the comet's coma, the solar wind being a stream of electrified particles being sent out by the sun all the time in all directions. The dust tail is produced by the sun's light striking the coma and driving the dust particles outwards. And that's why comet tails always point more or less away from the sun. At the moment, Halleys Comet is moving outwards, and so it's traveling tail first. The solar wind interacts with the cometary dust, and the solar wind is variable, gusty if you like, and this causes marked changes in the comet's tail. Giotto has already passed through the bow shock set up by the traveling comet, and we're getting ready for the main encounter. So let's consult the experts. What do they feel?
Well, I think this is the most exciting part of the mission. The spacecraft, of course, is now going to start seeing the dust. The instruments are now really going to start earning their money. The dust will start to increase significantly now, and it'll be starting to make the spacecraft wobble. So we hope we can maintain the signal, but at the same time, we're hoping we can see the nucleus of the comet with the camera.
I'm hoping to see what the comet really looks like. So far, we've never really seen a comet. We've seen the dust cloud that envelops comets, and even those from a great distance.
We have preconceived ideas about the nature of comets. We believe that there's a comet nucleus in the center. We have some ideas about the origin of comets. We've worked for years on the composition of the gas and dusty atmosphere. We have pretty good ideas how much dust and gas to expect, but I'm sure there will be major surprises.
I am truly excited because it was 36 years ago that I first published my conclusions that the comet, the real comet, the nucleus, was made of ices and dust. And now we will be able to see what such a nucleus looks like.
Quite apart from the camera, Giotto carries many other experiments, most of them arranged on a necklace round the spacecraft. At the present moment, we can only speculate as to what a comet's made of. Giotto ought to tell us. We'll be studying the dust and the magnetic fields that are so important in tail production. We'll be looking at the chemistry and composition of the comet, its atoms, molecules, and ions, which are incomplete atoms. Plasma studies. Plasma has been defined as the fourth state of matter, the others being solid, liquid, and gaseous, and is made of broken up pieces of atoms. But to demonstrate just what plasma is, let's go over to James Burke, or rather, see what James was doing in the courtyard of the old Royal Observatory a few hours ago when it was still daylight.
I'm doing it here in the freezing courtyard because, as you'll see, they didn't want to risk burning Greenwich down. Plasma, those broken up pieces of atoms that Patrick was talking about, make up about 90% of the universe. In this case, the plasma in question is caused by the solar wind, a cloud of superheated gas exploding at a million kilometers an hour out from the sun all the time. Now, the tremendous temperature of the sun strips the electrons from the gas atoms, and atoms without electrons are called ions. On board Giotto, the energy levels of those ions is being measured by a British experiment from the Mullard Space Science Laboratory. In essence, this is how the experiment works. This flame represents the hot gas plasma. And if you use this generator to send a charge through these plates and then through the ions in the flame, you can deflect the ions like this. Watch it being deflected to the left. It looks like wind, but in fact it's an electrical charge. Look, I'll do it again. And it's deflected. Now, if you measure how much charge causes how much deflection, you know how much energy the ions have, and you've measured the energy of the plasma. Now, that is basically how the plasma instrument on board Giotto works. This is where the plasma experiment sits on the spacecraft, and in fact it was switched on out in space some time back. The leader of the plasma analyzer experiment from Mullard is Alan Johnston. At his lab, he prepared his standby instrument for Giotto. This is the voltage generator. And these are the plates across which the electrical charge is applied. They're mounted on the particle detector itself. The plasma particles stream into the instrument and get bent towards the detector. Change the voltage, and you tune the instrument to measure the energy of different particles.
Well, some time ago, Giotto was hit by a huge shock wave. This is what it looked like on the computer printout. Let me stress that it didn't cause any damage because the density of the material is so low. Since then, within the last few hours, we've had some new information. Okay. Alan, what are your results so far?
Well, we've now been detecting the comet for more than 30 hours. We first found it at 4 o'clock yesterday afternoon, and it's gradually been increasing in intensity ever since then. And at about 8 o'clock this evening, we saw the first signs of the bow shock, and the bow shock turned out to be about 200,000 kilometers thick. And once we'd passed through the bow shock, we found, in fact, that it, instead of being more turbulent as I had expected, so far it's been quite a bit smoother, but hotter.
Well, you're using plenty of graphs. What exactly do they mean?
Well, we've got two to show on the screen here. This first one shows some of the different masses of ions that we're detecting in the comet. There's 4 frames there, each one taken successively, one after the other in time, and each one shows hydrogen ions and alpha particles from the solar wind in the bottom left-hand corner where it's red and green, and cometary ions in the top where it's blue. And one of the interesting things is that we're seeing particles at a mass of 8 where we didn't expect to see them.
How do you assess your results?
Well, they're very interesting. They're going to take a lot of analysing, but they're extremely interesting.
I imagine you expect better results from this as Giotto closes in toward the comet?
Yes, we're expecting things to change very rapidly in the next hour, and especially in the last 2 or 3 minutes just past midnight.
Patrick Moore was talking there with British scientist Dr. Alan Johnson. The object of all this attention has been ploughing through the darkness of interplanetary space for most of the last 76 years. The comet's fame comes from a fortunate combination of circumstances. It's bright enough to be easily seen, and it comes back regularly to the vicinity of the Earth. No other comets do both. The bright ones don't return, the ones that come back are faint. It's time, I think, to take a look at the known history of the comet and at how it came to be called Halleys Comet.
本类型膜类会小者受传成会经天 This is the first certain record of Halleys Comet.
Produced a rash of forgettable songs and the comet emblazoned on every conceivable product. Future archaeologists will have little trouble finding evidence of just when the comet. This is a negative of the first sighting of the comet that time round, as seen on September 11th, 1909. Over the months, it waxed into a most impressive sight, remembered vividly by many people still living. These pictures were taken at Sydney Observatory. The brilliance of the sight resulted from the comet being quite close to the Earth as it rounded the sun. We actually passed through the tenuous tail of the comet. After a few months of glory, the comet faded again, dwindling once more to a speck among the stars, and was soon lost to human knowledge for another 7 decades. Its next visit was destined to be less spectacular, but far more important. Now they brought change, mostly for the worse, with war and pestilence. In medieval times, the unexpected arrival of comets, the word actually means hairy star, and their often awesome appearance led to belief that when a comet was seen, some disaster would follow. Civil strife, panic in the streets, plague and cataclysmic events, the deaths of kings and of emperors. When Halleys Comet appeared in 1066, it was taken as an omen. The flaming star was recorded on the Bayeux tapestry. The inscription says his kingdom and his life. The Florentine painter Giotto saw the comet in 1301 and put it into his painting about the 3 wise men visiting the infant Jesus. Giotto made the comet the Star of Bethlehem, announcing good news to the world. Comets were feared because they seemed unpredictable. No one understood them. The learned man Halley, the second Astronomer Royal. It's appropriate, therefore, he should have the most famous comet named after him, though he did not actually discover it. To the solar system, to the laws of gravity and motion recently discovered by his friend Isaac Newton. He saw that under the influence of gravity, the comets followed curved and apparently parabolic paths. Pushing on, Halley found something most remarkable and unexpected. A comet seen in 1682 proved to have a very similar orbit to one seen 75 years earlier in 1607, and to another seen 76 years earlier again in 1531. Halley's hunch was that those 3 comets were in fact the same comet, returning to the vicinity of the Earth each 75 or 76 years. If that was so, comets were not wild bringers of ill fate, but well-mannered celestial objects circling the Sun in predictable orbits. Throughout 1758, astronomers sought the predicted comet, but it was almost gone before anything was seen. Then just before Christmas, a comet was sighted by a German farmer, and Halley's immortality was assured. The comet has been called Halleys Comet ever since. The last 30 returns of the comet are now on record, some much more spectacular than others. In 837 AD, the comet could be seen in the daytime, and its tail stretched halfway across the sky. But scientifically, the current visit of 1986 will be the most memorable, being the date of the first encounter. That first encounter with Halleys Comet took place yesterday, centred on the Giotto spacecraft. So let's go back to James Burke and Patrick Moore. First to James and the threat posed to the spacecraft by grains of dust.
Well, there's now less than an hour to go and 231,600 kilometres to go to closest approach. As you can see on the left, there's time to go to the closest point, and on the right, the distance. And from here on, from this distance out, to the problem of dust becomes the major test of the mission. The first impacts from the dust cloud in the coma around Halley were predicted to start just a few minutes ago, and we've heard that that's exactly what's happened. Let me remind you of what's happening out there in space. Giotto is heading in towards Halley like this, with its protective dust shield forward, and I'll get back to that particular dust shield in a second. There you can see it spinning around with the dust shield leading. Now, the theory is that the dust I'm talking about happens as a result of the sunlight evaporating the icy surface of the nucleus of the comet and the explosion of superheated gas pockets in that surface, sending the dust shooting out in great fountains to spread perhaps as far as, 100,000 kilometers out round Halley. I say it's all theory because nobody knows. That's one of the things we're hoping to find out tonight. But the size of the dust particles in that maelstrom are known. They're anywhere from this size, the size of a dried pea, right down through sand grain size to tiny particles this size, so small that they almost smudge when you move them around, and beyond that to the size of the particles in the smoke from a cigarette. Now, those dust particles are killers for 2 reasons. The first is communication. You see, the main spacecraft antenna, this dish here, is sending all the data and the pictures back to the receiving dish in Australia, back on Earth, 130 million kilometers away. Now, the distance involved in that communications link is so great that it needs pinpoint accuracy for the antenna to make and maintain contact. 1 degree off, that much, and we lose contact. And an impact from one particle this size hitting the edge of the spacecraft could knock Giotto off-center enough for the signal beam to miss the Earth. The second danger to the spacecraft is less, shall we say, subtle. Particle impact could just destroy Giotto. That's why there is a dust shield, or rather, two of them. An outer shield here, 1 millimeter thick, made of aluminium alloy, like this. And an inner sheet, 25 millimeters behind it, itself 12.5 millimeters thick, a backup shield made mostly of bulletproof plastic laminate to take the force of the particles that are big enough to smash through the outer shield and hit this inner shield like in the form of a jet of high temperature vaporized material. And they're expecting plenty of that kind of activity. In fact, at worst, all the spacecraft has to do is just survive through that dust storm long enough to get in really close to the nucleus, to snatch its pictures and scientific data before it is possibly destroyed. And if you think I'm overdoing the drama bit, take a look at this. This is a piece of test material looking at the conditions that that forward shield would encounter, the thin aluminium shield. It's been scaled up because they can't shoot a pellet as fast as the spacecraft is going, so the whole thing's scaled up. This was made by a pea-sized object fired at 5 kilometers a second at this aluminium 8 centimeters thick, 8 millimeters thick. That is the same scaled-up effect of one pea-sized object hitting the forward shield, that thin 1 millimeter thick shield. Now, they're expecting many, many of these impacts, perhaps as many as 10,000 a second. The second test they ran was on the Kevlar, as it's called, the Kevlar backup shield, and here they used a laser to produce the kind of effect that the jet of high temperature plasma coming from the result of a particle having smashed through the front shield, the effect it would have on the Kevlar. And as a matter of interest, over here on the edge, there's a tiny detector, there are several of them around, as you'll see soon, that actually detect those impacts happening, and that was I was talking about when you were looking at the screen on which we will be able to show you the effect of those impacts as they happen because of computer generation. The key point, encounter, as you can see on the countdown, will happen 51 minutes, just under 51 minutes, and 213,000 kilometers from now. There are, as you would expect, from what I've said about the dust, several experiments on board measuring those impacts. 2 experiments registering impacts by the very small particles, and one run by the University of Kent for the bits large enough to call what they're expecting to make real trouble. Tony McDonnell leads this British experiment. It's called the Dust Impact Detector, or DID. Giotto's leading surface carries 3 tiny sensors. The inner shield carries 1 more. The sensors are miniature microphones to record the impact of particles hitting Giotto faster than a bullet. McDonnell's main problem is that he doesn't know just how big the particles will be, and will the twin shields be enough to protect Giotto? He tests the system with tiny glass beads. The mini microphones record the impacts, telling McDonnell the size and position of Halley's dusty missiles.
At the moment, the experiment's going very well. We're getting a high-level activity on the front dust shield, and this is showing that some of the particles are going through to the rear, and it does so show that the meteoroid protection system is working. Looking at the next few minutes, we're going to find the activity increasing and several thousand per second later. What's important is that we get through the point of closest approach and come out of the comet on the other side.
So you see there from what Tony McDonnell was saying, they're already getting impacts that are going through that front shield. By the way, it's called the sacrificial shield, and now you know why, because even this far out, 206,000 kilometers with 50 minutes to go, they're beginning to get impacts going clear through that front shield. Well, the predictions are, in fact, that they will hit a fair amount of these medium-sized particles early on, and then hopefully the impact rates ought to drop off a bit before those rates start to rise inexorably towards maximum density as we move towards encounter. Question is, will Giotto survive long enough to get close enough to learn something about what that nucleus is made of? Patrick.
The nucleus is, after all, the heart of the comet, and that's what the scientists here are trying to study above all else. Up to now, we've been reduced to little more than guesswork. Some years ago, it was thought that a comet might be a flying gravel bank. But now there's good circumstantial evidence that the nucleus is an icy mass, about 6 kilometers in diameter, spinning round in something like 54 hours. If we knew the size of the nucleus, we could work out its mass and its volume, and we could then estimate how long Halleys Comet will last before all its ices are used up. And present estimates range between 50,000 and 200,000 years. The camera was switched on again for the encounter 5 hours ago, and this is the best picture it's sent back so far. Well, dust or no dust, the camera is certainly sending back results, and there's quite a difference between this picture and the last one you saw. Now remember, Giotto is approaching the comet at something like 68 kilometers per second, and that makes a tremendous difference even over short periods. And now we can actually start to see structure in the comet. Once again, let me remind you that these colors are not real. They indicate differences in brightness and therefore differences in density, and there's no doubt that the densest and brightest part of the comet is that white blob you can see at the bottom, and that is where the nucleus is, even though we can't actually see the nucleus itself at the present moment. And then red, blue, green, and purple indicate lower and lower light levels. So at the present moment, the camera is sending back good results. And of course, as it goes in closer and closer, we shall get better and better results. And one thing we know, though, for certain now, the camera itself is working really well. James?
Well, this is where the camera sits, with its mirror poking out from behind the dust shield. That camera's job, of course, is to detect the nucleus and then take as many color pictures of it as it can. The delicate camera is Giotto's most immediately dramatic experiment. Already it's sending back a continuous stream of pictures. This is Giotto's eye, giving scientists the chance to see a comet's nucleus. The camera can be rotated to take pictures both ahead and behind Giotto as the spacecraft skims close to Halley. The hope is that the camera will survive the dust storm, mounted as it is behind the bumper shield. Its pictures in 4 colors allow scientists to establish the size and shape of Halley's nucleus. From 500 kilometers away, the camera can pinpoint an object a mere 30 meters across on the comet's surface. All this while Giotto itself is spinning 4 times a second. Incoming light, and maybe dust, bounces off a steel mirror into a telescope. The image is then focused onto 2 charge-coupled devices, or CCDs, which take the picture. This is what the charge-coupled device looks like. Hundreds of lines of light-sensitive spots, and as the spacecraft rolls, I'll use my finger to imitate that, and the image moves across the camera mirror, one thin cross-section of the image at a time is stored on here for a few microseconds, and the data sent back to Earth. And then the next line, and so on. It's hairy stuff, but that's quite a camera. I mean, it could, for instance, get a clear shot, they say, of a mole on the face of the pilot of a Concorde going by a mile away at the speed of sound, which is great if the Concorde isn't in the middle of a cloud, which, according to last week's Russian pictures, Halley is. Now, from 8,000 or 9,000 kilometers, the Russians weren't expected to see the nucleus. Even so, the cloud they did see looked very small and very dense. When all the Darmstadt scientists got together to discuss that particular matter, all hell let loose. Some wanted to send Giotto very much closer than the planned 500 kilometers. But the camera team naturally wanted to play it safe and steer clear to over 1,000 kilometers away from anything that would sandblast the motor of their camera. With 2 or 3 times as many camera scientists occupying far more space than any other experiments, it would have made it a waste of money to build a spacecraft that could go to half that distance, to 500 kilometers. So in the best European tradition, they compromised. They chose a target distance the other day of 540 kilometers, almost exactly what had been originally intended. Just now, as you can see, the distance to go is 185,000 kilometers with just under 45 minutes, and closing. What are the pictures like from this distance? Patrick?
Well, they're pretty good, and the camera is working very well. But one thing we have got to remember, as Giotto goes into closer approach, it makes a very, very rapid pass of the nucleus, only about 10 seconds or so. And altogether, Giotto spends only about 4 minutes closer into the nucleus than Vega did. So it's got to be a very fast business altogether. But all the same, they seem fairly confident that they will get better pictures than Vega obtained. The procedure, by the way, is for Giotto to send back a raw picture, and then, after a few minutes, it's enhanced, so you get a bigger and better view of it. And that's the way it is done, and all the pictures you're going to get tonight will be on this false color principle. And I say again, the colors are not genuine. But already the comet is showing structure, and as we get closer and closer to the nucleus, there's no doubt at all that these pictures will gradually improve. So is the nucleus really a dirty snowball? That was the theory put forward by Dr. Fred Whipple over 30 years ago. You're still confident about it?
I certainly am. I think we have a great deal of evidence to prove that it is true. Particularly radar observations, radio reflections from the nuclei of 4 comets showing that there is a discrete body in each one of them.
What evidence are you looking for from Giotto?
Well, particularly the shape and the surface characteristics of the nucleus, because so far this has been entirely a matter of imagination. Now we will see the real thing.
So you're really hoping to see the nucleus tonight?
I'm really expecting to see it tonight.
Well, some people have suggested that we won't because it'll be hidden by dust.
Well, there will be some loss of visibility due to dust. There's no doubt of that. But I think that because of the protection that the camera has in Giotto, there's a good chance that we shall see at least some details of the nucleus.
If we're going to make really close-range studies of the nucleus, the first thing we have to decide is exactly where the nucleus is. And remember, it's well and truly hidden by the dust. There's another complication also, the jet problem. Gases escaping from the nucleus which push it around and may also be a hazard to Giotto. Dr. Rudiger Reinhardt, could they possibly endanger the Giotto mission?
They could very well endanger the Giotto mission, although one has to say that the dust jets as we see them consist of dust particles in the range of 1 to 10 microns. These particles are of no danger to the Giotto spacecraft. However, associated with these visible jets are regions of dust particles which are not visible, large dust particles, and these could endanger the Giotto mission.
Could they put it off course?
Not off course, but they could disturb the spacecraft attitude, and then the telecommunications linked to the Earth could no longer be maintained.
Patrick Moore there with Dr. Rudiger Reinhardt, and before that with Dr. Fred Whipple, patriarch of comet lovers and inventor of the dirty snowball. Giotto is not alone in space in its probing of Halleys Comet. While the United States has not sent a probe to meet the comet, it has turned the cameras of a spacecraft currently in orbit around Venus onto it, and another American probe will scout the general vicinity of the comet in a month or so. But a far more active role in the Halley Watch is being played by Japan and the Soviet Union. Their probes, launched last year, joined Giotto to form the biggest and best equipped welcoming committee the comet has ever had.
The Russians launched their Vega 1 space probe in mid-December 1984 and Vega 2 6 days later. The start of a 14-month journey to take the Vegas to within 9,000 kilometers of Halley. The slim solid-fuel rocket carrying Japan's second Halley mission stood ready for liftoff last August. For the Japanese, Project Halley is the first venture into interplanetary space. Their main spacecraft was aimed to pass 150,000 kilometers from the comet's nucleus. The Japanese Planet A spacecraft's mission to monitor the comet's vast ultraviolet corona. The European spacecraft, Giotto, is by far the most ambitious of the multinational group. Tonight's encounter comes at the end of a journey that started last July in Kourou, French Guiana. Sited near the equator for maximum benefit from the Earth's rotation at liftoff, the Kourou launch pad is the home of ESA's Ariane rockets. Giotto was to be carried on the first stage of her 700 million kilometer space journey by Ariane flight number 14. July the 1st, launch day -1, halfway through the long countdown procedure. Ariane is ready to go. For Giotto's scientists, 5 years' work now rests with the Ariane launch engineers, and Ariane rockets had been known to fail in the past.
Plus 3,4 secondes, l'ouverture des crochets, suivi du décollage.
First stage servo motor started.
Les paramètres et les mesures sont actuellement corrects.
Attention pour H0. Final arming, ready to go.
Les derniers armements ont lieu en ce moment.
10, 9,
Décompte final.
8, 7, 6, 5, 4, 3, 2, 1, top. Ignition. Ariane first stage ignition and takeoff. Takeoff and décollage. First stage flight. Début des manœuvres de roue libre.
Safely on course. The Japanese planet A arrived 5 days ago, closing with the comet at over 70 kilometers a second and successfully measuring Halley's ultraviolet output. The Russian Vegas moved in last Thursday and Sunday, sending back pictures and pinpointing Halley's precise position. The Vegas narrowed down the path of Halley's orbit by a factor of 3. So Giotto is being guided with amazing accuracy for the closest encounter. Tonight sees the culmination of that mission as the small spacecraft spins the last kilometers towards the comet's very heart. Just a few moments from now, Giotto meets Halley. So, how did the Pathfinders get on? The Russian Vega spacecraft are vital to the success of the International Halley mission as a whole, and of course for Giotto in particular. Patrick.
Both the Russian probes, the Vegas, have been very successful. They're also of tremendous value in the Giotto mission, because now we have at least some idea of what to expect. Both the Vegas bypassed the comet between 8,000 and 9,000 kilometers. The instruments recorded strong electric fields and electron currents. The plasma density was measured, and there were indications of a tight inner dust shell. Vega 2 took some fascinating pictures. Look at this. It seems rather like a double nucleus, although there must presumably be some sort of connection between them if it really is a double nucleus. Let's hope Giotto will tell us more. But there's always the dust striking the spacecraft at 68 kilometers per second, and it did do some damage. Remember, though, that the Vegas weren't equipped with dust shields, anything like so efficient as Giotto's, so they were much more vulnerable.
Now, the Japanese have been getting a great deal less publicity for their encounters, but they too have been getting some extremely interesting results. At the Institute for Space and Aeronautical Science in Tokyo, results from the twin Japanese spacecraft have been coming in since mid-December. Spacecraft Sakigake has been measuring Halley's interaction with the solar wind from a distance of 7 million kilometers, while spacecraft Planet A has been taking ultraviolet pictures of the comet's hydrogen corona. The UV pictures confirm that Halley's hydrogen cloud is over 2 million kilometers across, and that the comet rotates once every 53 hours.
The Japanese have been busy not only in space, but on the ground as well. For some time, a team has been camped up at Siding Spring Observatory in upcountry New South Wales, where the skies are reputedly the darkest in the world. Siding Spring Mountain is home to a number of telescopes, including the great Anglo-Australian telescope. The Japanese technicians have coupled together telescopes, image intensifiers and TV cameras to produce the best pictures of the comet taken from the surface of the Earth. Well, what did you think of that? It's time we were back in Darmstadt. Throughout the morning, Giotto continued to head for its target at blinding speed. So let's find out from Patrick Moore how things were progressing.
Well, in point of fact, we're now within a very few minutes of close to encounter. We're entering the most exciting time of all. Let me show you how they enhance the pictures. The picture comes through, and then it can be jacked up like this to bring out the detail, as you can see. So the raw picture that comes in bears only a little resemblance of what you finally get. The picture can be improved by out of all recognition. And that is, in fact, how it's done. And another picture has just come in. Look at that. Once again, this is a false color picture, and that red blob must indicate the position of the nucleus. And before very long now, we shall know exactly what that nucleus is. And Giotto at the moment is still going. It's still going, and we're very close now to the vital moment as it speeds inside and makes its closest pass of the nucleus.
Most of the action in this encounter was to be crammed into the last few minutes. As the probe neared its objective, data would be streaming back much faster than it could be analysed. There was also the underlying uncertainty about the fate of the craft. Would it reach the target still in full working order? Well, no one knew quite what to expect, and that added to the mounting excitement. So it's back once more to Darmstadt and to Greenwich. The countdown clock has still just under 10 minutes to run. The point of closest approach is 41,000 kilometres away and closing fast.
We're getting this, finally getting this computer-generated data coming back in about the amount of damage that's going on here. And Tony MacDonald, I gather you're out there talking with Patrick right now. Are things hotting up for you, or are you still as happy as you were?
Well, very much so. They are now within a minute or so of closest approach, and we're very glad that Tony MacDonald has taken time off at this particular moment to come and join us. Tony, very near the crisis now. What's the situation?
Well, we're a little bit behind in terms of information coming back, of course. The probe is actually at its probably worst position now, but in fact the data's 12 minutes behind. The data's building up. We know that the shield is lasting. In fact, it's going to survive, and I think the chances for getting past and getting data on the way out are very, very good.
You are, in fact, you think, are now over the worst period?
I think we are indeed, yes.
So, in fact, the shield has really done all and more than was expected of it.
Superb indeed, yes. The dust cloud is, though, very much smaller than we'd anticipated.
Very much smaller, or just marginally so?
Perhaps a factor of 2 smaller.
And what about the actual distance of the dust from the nucleus? Is that smaller as well?
Yes, indeed, yes. It took us, indeed, at least an hour before we got our first impact, so very much smaller.
Have you had any major impacts at all on the spacecraft?
Not any which have rocked the spacecraft in any way, and therefore the stability of the spacecraft is good. It's going on the same course, good pointing direction. The camera will get good images.
Well, as we know, you know better than I do, the bumper shield was designed in 2 parts. A thin one to break the emitted particles up and produce them into a kind of a spray, and that principle really paid off.
We've got to evaluate the data before we can really confirm it, but yes, indeed, it looks as if it's doing very well at the moment.
What about the numbers of really large particles? In view of the fact that Giotto has escaped so far, do you think they really are much rarer than was expected?
Well, at this time, the largest particle probably has indeed struck the comet, the space probe indeed, but we don't know yet. We've got to wait 6 minutes for that information.
We have indeed. And, of course, you're not quite out of the wood yet, or rather out of the dust storm, because you may be just about passing closer to approach now, but then there's the outward journey. Do you think there's any danger of being struck on the outward journey?
That's supposed to be, I think, an easier ride than the inward journey. The comet is a bit shorter on that side because of our approach direction.
And, in fact, well, therefore, it does seem that all is going to go well.
I think so.
Well, Tony, thank you very much.
A pleasure.
And, in fact, we have here got pictures of the control room where everything at the moment is going on. After all, is the nerve centre of the entire operation, as you can see. And you can see there a picture on the control room screen coming in from Giotto. At the moment, it all seems to be going well, and I imagine there's rather a feeling of considerable relief down there at the moment, because if all the indications are as we believe, then Giotto will in fact survive the encounter and will be able to pass on to possibly to other comets, which is probably something that most people, well, everybody wished, but I don't think people were entirely confident about right up to the last moment. So I imagine down there now that there's all kinds of discussions going on, and the revelation that the dust cloud is smaller than we expected really is, I think, very much of a surprise, because after all, Halleys Comet has always been regarded as a very active comet. It's a large comet. It's a very large comet, and we are now just about at closest approach. But, of course, remember, the distance of the comet and the probe from us at the present moment is something like 150 million kilometers, and that's just about the same distance as the distance between the Earth and the Sun. And light and radio waves and messages take something just over 8 minutes to cover that distance. So they 8 minutes to cover that distance. And so it won't be for another 7 or 8 minutes that we'll know whether Giotto really has survived. But all the indications are that it has. James.
Yeah, well, here in Greenwich, we're about to see some of the pictures that have been coming in. And perhaps I could ask you, Alec, to start commenting on what you think they're telling us. Can you see enough at all?
Well, it's difficult to really appreciate what one sees in a picture of this nature. It's in false color. The brightest bit is the red bit, and that looks quite small, but I can't tell you exactly how big it is. That has to be really processed properly. But the pictures look of very high quality indeed.
Do you think that might be because of this business about their having gone through perhaps the sort of last major shell of dust and got themselves into, as it were, a clearer zone?
Well, they certainly look a lot clearer than they did before, and a lot more compact there in the middle. And if anything, you'd expect it to be larger being closer. So I guess that is what's happening, that the dust is clearing, so to speak, and we're seeing further into the nucleus than before. Maybe we are seeing the actual nucleus, but it's hard to say at the moment.
Yeah, the point is, of course, these pictures are pictures that have come in some minutes ago. They're not, in fact, as we can see, we're 21,000 kilometers to the point of closest encounter. In fact, these pictures may have come from how far back? How long do you think it would take them to get these pictures processed to that stage and on this screen?
Well, the light travel time is about 8 minutes, and it'll take a few more minutes perhaps to come out on the screen like that.
To that, so those pictures you reckon could be anything about 15 minutes back?
Yes.
The quality of those pictures, Jim, does that mean that you stand a better chance of getting the kind of analysis you need than there would have been if the dust had been higher than was expected? Sorry, yes, if there's been a lot of dust?
It means that Giotto has a much better chance of getting right through, yes, than we would have said perhaps an hour ago.
What about this business of the Russians saying, Jack, that they thought that there might have been a very dense cloud of dust just above the surface of the nucleus? Did I not hear that claim?
You did indeed, yes. That's their interpretation. They produced slightly different interpretations from the two Vega spacecraft, which went through a few days after each other, but about the same distance away. But the interpretation they put forward after the second one was that there was a cloud, an egg-shaped nucleus, about 6 kilometers across, so a bit less than 5 miles. But what they were seeing, they thought, was a dust cloud around a real solid nucleus, which was perhaps 2/3 to a half that size. Yes. Now, if that's the case, we really are in serious problems, because one of the great things we expected to get out of this was a solid nucleus.
I'm sorry to interrupt you, because these are live pictures coming down from Giotto now. Alec?
Well, it's progressing, as far as one can really judge it from those pictures. They look like they've got more structure than they had before.
What does that mean, they have more structure?
Well, that means we're seeing more detail. We're getting closer, and we'd expect to see more detail, but I think we can see rather gross structure. And of course, the nucleus would not be uniformly white ice, a uniformly white ice ball or something like that. It would be very murky and dust and grey in places and so on. That's what looks like we're seeing. If we're seeing the nucleus, I'm not suggesting we are.
No. Can I ask you, the general blob, presumably the blob to the top left there is a dust or some artificially created thing, but the general blob that we're looking at, the orange-coloured blob with the core, approximately how big across would that be if you were, say, seeing pictures that came in that were taken 8 minutes ago and therefore, say, about 50,000 kilometres out? Do you want to make a guess?
I can't make a guess, I'm afraid. And it's difficult anyway, because those are contours we're seeing, and we can't really make out which contours we see.
Sorry, maybe I should ask the question more clearly. Are we actually seeing well inside the head of the comet that we would normally see if we looked up on a clear night and saw it? I mean, we're looking at it well inside that, are we?
Yes, we're certainly looking well inside it. But just how far inside, it's very difficult to say from those pictures.
Yes, right. Let me go back to Darmstadt with Patrick. Patrick.
Well, we're delighted that Alan Johnson to be able to join us again. Well, Alan, this is the great moment. What do you make of it?
Well, it's been very exciting. We've got some very interesting data. We've just seen the ions disappear from the view of our instrument, and so that means we're inside the contact surface very close to the comet. And we're now just seeing the final pictures from the nucleus.
And we really are seeing the nucleus itself, you think?
I don't know. We'll have to wait until we see the pictures in more detail before we can tell exactly what part of it is the nucleus.
It seemed to be irregular in shape, and that could, I suppose, tie in with the results obtained earlier on by the Vegas.
Yes, I'd expect it to be irregular in shape. Certainly, it's always been thought of as probably irregular. And that's the picture that's coming through now.
Does that give you any clue as to why one side of the comet is so active and the other apparently passive?
Not yet, I think. If it's irregular, it certainly tells us it's not a uniform body. But to tell exactly why the reasons are that one side is active and the other side is quiet is beyond us at the moment, I think.
Well, when we came on the air, we said that we hoped that just after midnight we would be able to see the actual nucleus of the comet. All in all, do you think we've done that?
I don't know. We'll have to wait and see.
Gentlemen, can I interrupt because... Hello, this is James in London.
Getting some very interesting
Can I interrupt because I hear that we're getting live pictures in from the dust detecting equipment from the experiment, looking at what's happening to the shields at the moment, and you can see there the impact actually being generated in real time.
Is that going to be a problem, do you think?
Waiting to see.
This is... we're not sure what that picture is there. That obviously it looks like something coming down from the camera, but why it's coming in that particular format. I don't know. Alec Boxenberg, do you want to guess about that?
I think there's some interference there that is making it very confusing.
And so, in quite dramatic fashion, the screen went black. With only 2 seconds left on the countdown clock, and with Giotto still some 140 kilometres short of its point of closest approach, the pictures simply stopped arriving. For quite a few minutes, confusion reigned at Darmstadt, in Parks, in the BBC studios, as people tried to work out what had gone wrong. A vital clue came from the record of the dust detection experiment. Whereas for most of the inbound flight, this had recorded fewer impacts than expected, there was a real surge in dust noise just prior to the screen going black. It seemed that having got through the region where the dust was expected to be thickest, Giotto had run right into a hail of dust particles, all travelling at 70 kilometres a second relative to the spacecraft. There were three possibilities. The first was that the spacecraft had been totally destroyed. That was always a chance, and indeed, as one scientist said to me straight afterwards, that was Giotto's destiny. It had been designed to go in very close to the action to collect the maximum data, and that meant almost certain destruction. Secondly, perhaps the Giotto had merely been disabled in some way, perhaps fatally, perhaps not. And thirdly, this was the option everyone hoped for, there was a chance that the dust impacts had simply knocked Giotto out of alignment, so that its radio antenna was no longer pointing at the Earth. The transmitted signals would then not reach Parkes. If this third possibility was the right one, then all was not lost. Giotto had a self-writing program in its computers, and after 10 or 15 minutes, it would trim its attitude, find the Earth again with its antenna, and the signals would come through once more. Well, those were the possibilities, but for the first few minutes after the loss of signal, nobody knew what was right. Confusion reigned. In the Darmstadt studios, Patrick Moore cornered Fred Whipple to find out his thoughts on the outcome.
And after all, who better to join us at this critical juncture than Fred Whipple, the man who worked out the dirty snowball theory of the comet? Well, Fred, you said earlier on that we were going to see the nucleus tonight. Did we?
We did. I'm quite sure we did, yes.
It was, in fact, that red mass that we saw on the screen.
Well, it will have to be analyzed in more detail without all of those pretty colors, which may mislead the public as to the nature of a comet nucleus, because it's really a very black, gray, like perhaps black velvet or charcoal.
Well, we have emphasized all the way through this program that these colors are not genuine. You don't really see a comet like that. But from those pictures, what can you tell about the composition of the nucleus? Can you think it can definitely confirm finally your dirty snowball theory?
Well, I think that we have enough evidence that will come out of the spectroscopic evidence, the nature of the gases, and the analysis of the dust to show it conclusively. Yes.
Of course, it's not only the camera, as we know. I mean, the camera did magnificently right up to the time of closest encounter.
Yes.
Now, I imagine those last pictures that actually came back from Giotto were taken just about the time, and it was something like 540 kilometers away from the nucleus itself.
Or perhaps a little farther than that, but perhaps 1,000 kilometers, but something of that order.
But of course, it's not only those pictures that will help to confirm your theories, all the other experiments as well. Which do you think are the most important of those from your point of view?
Well, I don't know. There's several of them, of course, but I think the one that tells the composition of the gas will be in the final, when the final story is told, will be the most important.
Well, now come back to the matter of the moment. We have lost all trace of Giotto. What do you think has happened? Has the spacecraft been destroyed? Is it the cameras been put out of action? Or has the antenna been jolted so that at the present moment we're not receiving the signal?
Well, I don't think at this point I can answer that question. I think that will be a technical question, but I'm sure that the dust in the neighborhood of the nucleus did it and shows that comets are very dangerous when you go through them at 70 kilometers per second.
The justly pleased Fred Whipple with Patrick Moore. Well, as events in the next few minutes showed, Giotto is a tough little bird. The word came through from Parkes quite quickly that they had picked up the signal once more. Faint, but certain. Giotto was not, in fact, dead. It was still on air and collecting data as it's ploughed its way out of the comet. It had survived a passage through the very heart of the Halleys Comet, passing within a few hundred kilometres of the comet's icy core after a journey covering many millions of kilometres. In the control room at Darmstadt, they stood up and applauded, as well they might. They had plenty to cheer about. The very latest information which has come from our friends at Parkes, this came in just this afternoon, is that Giotto, although it has survived, is really in not very good shape. It's been pretty badly knocked about. For example, it's still tumbling a little bit and that's causing the signal to waver. The spacecraft is covered with dust. This is causing it to heat up. But the camera is functioning, but the main mirror has been pretty badly blasted. Perhaps the most interesting piece of information of all is analysis has shown that the particle of dust which knocked Giotto off its orientation weighed 8.5 grams and was big as a golf ball. It was a real biggie. None of the particles seen before that moment was anything like that size. Well, the Parkes dish stopped tracking the Giotto probe at 2:30 this afternoon. So in that sense, the encounter is over at last. Giotto has now fallen into an orbit around the Sun, and in 5 years' time, it will once more be back in the vicinity of the Earth. Well, it's not easy to sum up the achievement of Giotto, other than mere survival, so soon after the event. Many of the boffins are predicting quite cheerfully that it will take them years to work through the mountain of data that Giotto has provided. Even those pictures, which look so impressive in their rainbow colours, have had only the most elementary processing as yet. With the help of James Burke and one of his expert panel, let's take a closer look at one of the last images Giotto sent back before it fell briefly silent.
We've got now the first real enhanced picture available from the spacecraft. There you can see it. And would you care to comment on that, Alec?
Yes, I think it's a remarkable picture. There's clearly a lot of irregularity in the nuclear region there, and also a lot of surface structure that we saw before. It's much easier to see it in this picture that we're seeing now. But of course, we still have to, as has been said by many others, massage it further, and of course we can't really make out exactly where we are in the nucleus because the colour boundaries are a little bit confusing.
But sorry, you're saying where we are in the nucleus. You mean a large part of this picture could represent the nucleus itself?
Yes, most definitely.
In other words, we are looking at a partial view of the entire nucleus, you think?
No, I think we're seeing the nucleus within that picture, and it's probably in the area of the green part of the frame that you're seeing. But just where it comes in depends very much on where the colour boundaries are placed, and that is a matter of massaging. We'd see it more easily if it were black and white, but then we wouldn't see the whole depth of the image, and that's why we're seeing it in this false colour now.
It's worth remembering that Giotto, for all the prominence we've given it tonight, is only one element in a major international effort to uncover Halley's secrets. A number of nations were involved. There were probes in deep space, satellites in orbit around the Earth and around Venus, and many detectors on the ground. Through the joint efforts of all those observers, we know that as Comet Halley rounded the Sun, the cloud of hydrogen that closed it grew to be nearly 20 million kilometres across, 15 times bigger than the Sun, 1,000 times the diameter of the Earth. That its hidden frozen core spun on its axis once every 15 hours. That water boiled off from the nucleus at a rate of 50 tonnes every second. And that meant the loss of nearly half a metre thickness of ice and dust every day. That the core was a mere 5 to 8 kilometres across, chilled by its passage through deep space to a temperature nearly 250 degrees below zero. That one side of the comet was more active than the other, suggesting a surface with clefts and chasms, a hidden landscape that the fully processed pictures may reveal. Giotto, by flying through so close to the comet core, has given us a chance to taste the comet, to determine in detail its chemical composition. The lure of that is that comets are widely held to be deeply frozen leftovers from the formation of the Sun and the rest of the solar system 5 billion years ago. So comets are made of primeval stuff. The more we know of their makeup, the better we understand the history of the solar system and of our own planet. So before we go, let's take a look at the question I think everybody is asking, just where to look in the sky to see the comet now and say over the next month. We've prepared some star maps that I think should help. Right now you have to be up before dawn to see Halleys Comet while it's still dark, and since daylight saving ends in about 5 hours, that means being up before 4:30. Look due east. This map shows you some of the stars you'll see, particularly the curved line of stars like a question mark reversed, which is the constellation of the Scorpion. Below that is Sagittarius, which I've called the teapot. It does look a bit like a teapot on its side. And further down still the stars of Capricorn, another sign of the zodiac. Another guide is the Milky Way, which cuts right through these stars as a dim band of light. It's not much fainter than the comet, so if you can't see the Milky Way, you'll be struggling to see the comet with the naked eye. Go somewhere darker and clearer, like out of town. Tomorrow morning, around 4:30, the comet will be hanging in the sky well below the Milky Way and the teapot, about 40 degrees up, looking due east. The movements of the comet in the sky are a bit complicated. First of all, the comet is moving westward through the stars. The stars themselves are rising about 4 minutes earlier each night, and the sun is rising later. So on April the 1st, you can get up about 5 o'clock. Look due east, but much higher up, now 75 degrees, and the constellation will be lying across Scorpio and the Milky Way. It's then at its brightest, with the longest tail, but there's a last quarter moon not very far away. Thereafter, the comet takes pity on all sleepy heads and begins to rise during the evening. By April the 10th, the comet, still moving upwards through the stars, has almost cleared the Milky Way. At 8 in the evening, it's about 35 degrees up and to the southeast. The comet will be fading by then, but there's a new moon on April the 9th, so the sky should be dark. With the comet above the Milky Way from now on, it's time to name some more star groups. Over on the right, you can see the Southern Cross, and the star field through which the comet is ploughing is called Centaurus. The Scorpion lies below. By 8 p.m. on April the 17th, the comet has just about cleared Centaurus, still due east, about 50 degrees up. By now, the moon is growing bright again, moving east through the stars. On April the 24th, the comet is 60 degrees up at 8 p.m. and fading fast. The moon should be full that night, but it is in fact eclipsed, and so the resulting darker sky will give you your last real chance to see the comet before it departs for another 75 years. By the time Halleys Comet comes round again in 2061, we may know all there is to know about comets, and may be content to let it go by unmolested. If that's so, our descendants may care to recall that the first big step in that growth of knowledge was taken this time round with Giotto and all the other probes. In summing up this mission, I put it with that other great close encounter that took place this year, that between the spacecraft Voyager 2 and the planet Uranus in January. That too carried cameras and scientific instruments into hostile and uncharted regions of space, enhancing our knowledge of just where this planet stands in the scheme of things. Well, I hope you've enjoyed this coverage of the Giotto mission, the first ever encounter with the most famous of comets. From all of us here, good night.
Next week in Discovery, anyone can be a genius. The fascinating story of Dr. Luis Alberto Mercado, charged with raising the IQ of the entire population of Venezuela.